Okay, example problems with calorimetry. First problem. A spherical balloon with a diameter of 3 centimeters is heated until its diameter is 4 centimeters. The pressure inside and outside of the balloon is atmospheric pressure throughout the process. During the process, 5 joules of heat enters the balloon. How much does the internal energy of the balloon change? Alright, so what are we going to use here? We're going to use the first law of thermodynamics. The change in internal energy, which is what we want to find, is just equal to the heat that flows in plus the work done on the gas. Alright, and we're given the heat that flows in, that's just our 5 joules. So in order to find the change in internal energy for the gas, I just need to know how much work is done on the balloon as it expands. Alright, well, we know that the work done is just the integral, negative the integral of pressure d volume from initial volume to final volume. Alright? The pressure in this problem is constant. It's just atmospheric pressure, so that comes out of the integral, and we're just left with minus P naught, the integral from V initial to V final dV. That's an easy integral to do, so it's just minus P naught, V final minus V initial. So all we have to do now is find the initial and the final volumes. Alright? So what we're given is we're given an initial and a final diameter, so all we need to know for this problem is that volume of a sphere is 4/3 pi r cubed, or 4/3 pi diameter over 2 cubed. And so our answer for the work then is just going to be work is equal to negative atmospheric pressure. Volume final is going to be 4/3 pi. Let's factor that out. The final volume is going to be d final over 2 squared. And then the initial volume goes as the initial over 2. Sorry, that should be cubed. Cubed. Alright? And so that will give us the work done, and the change in internal energy then is just going to be the Q that we're given plus that work. Notice that the final volume is bigger than the initial volume. So this is positive. We have a minus sign out front. So the work done on the balloon is negative, right? The balloon is expanding. The balloon is doing work on the environment, which means positive work on the environment, which means the environment is doing negative work on the balloon, right? If I squish a balloon, I'm putting energy into it. If the balloon expands while I'm holding it, it's putting energy into me. Negative work is being done on the balloon. Positive work is being done on the environment. So the balloon is expanding, which means it's doing work, which means the work being done on it is negative. And just to keep all of our signs straight, usually we like to think of work as being positive when energy is entering the gas. Alright, so what happens is heat flows into the balloon. Some of that energy that comes in as heat leaves the balloon because the balloon is doing work on the environment. Negative work is being done on the balloon. And what doesn't leave ends up as change in internal energy. Alright, this is an example of a problem with an isobaric issue. Alright, now hopefully you understand the derivation. Going back, why does work equal negative the integral of P dV? Well, because pressure is force times area, alright? Right? And if I take area times dV, the change in volume, imagine if I had a piston. This is just review, this is not part of the problem, but just reminding you where this comes from so it's not mysterious. Alright? Work is force times distance, so a little bit of work is force times dl. Alright? But if I take the change in volume, dV, that's just dl, right, times the area. Sorry, pressure is force divided by area. And so that's where the area comes from. So basically we're just taking work as force times distance, and we're writing the distance in terms of the volume. That works really well with a piston, right, where we know that it's just expanding in one dimension. We could have just done this equation right here. When you have a balloon that's expanding in all different dimensions, it gets a little more complicated, so it makes more sense to write it in terms of change in volume instead of change in distance. Just that's where that equation comes from. Let's look at our final problem here. A gas is compressed from a volume of half a cubic meter to a volume of a quarter of a cubic meter. During the process, the pressure is given by this equation here, where P0 is atmospheric pressure. How much work was done on the gas? All right. Once again, the work done is just minus the integral of pressure dV from V initial to V final. In this case, V final is smaller than V initial, so we expect this to be a positive work done on the gas. All right. Once again, the work is just this integral, and the integral of P dV, if I plot pressure as a function of volume, all right, we're doing something like this. We're just doing this integral, and as you recall, the integral is just the area under a curve, so we could kind of graphically illustrate the work by plotting the pressure as a function of volume, and then just say, oh, the work is just the area under that curve. But let's actually do that integral. So we're given an equation of how the pressure changes and the two volumes, and so we can just plug this in, right? Work is equal to minus the integral of pressure dV from V initial to V final, but we know what the pressure is. All right, we're given V, should call that VB, right? They can't be the same. All right, we have an equation here. It's P0 VA over V dV, and our initial pressure, our initial volume is VA, and our final volume is VB. So we can just go ahead and do this integral, right? VA and P0 are constant, so they come out. And then it's just the integral from VA to VB of dV over V. And I know that the integral of dV over V is just the natural log, right? So P0 VA natural log of V evaluated from V equals VA to VB. When you do integrals that turn into natural logs and you have something with units, it gets kind of weird. You may think this is weird, right? Because what are these units? They could be cubic meters, cubic centimeters. I can convert my units. How do you take the natural log of something with units? Right? If I just plug a number in here and I get my natural log, I'm going to get something different depending on what units I use, right? I plug the same volume in here in cubic centimeters, cubic meters, liters, gallons. I'm going to get a different result, all right? Natural logarithms don't take units. But it turns out everything works out nicely because we're taking a difference, right? So when I actually calculate this, this is going to be P0 VA, negative P0 VA, natural log of VB minus natural log of VA. And if you'll remember, your logarithm identities, when you take the difference between two logarithms, it's just the logarithm of the ratio. So this is P0 VA natural log VB over VA, and the units cancel out when we do the ratio. I bring this up because this will happen multiple times in this course. We'll end up taking natural logs and applying limits to them, and we'll be concerned that there's units in the natural logs, but it doesn't matter because we end up taking a ratio in the end. Anyway, there's the work that is done. You can plug the numbers in and get your answers. But first of all, before we do that, let's think about this. Does this make sense? If the final volume is smaller than the bigger volume, we've compressed the gas, which means we've done positive work on the gas. Am I going to get a positive number here? I have a negative sign out here, but the final volume is smaller than the initial volume, all right? And that means when I take my logarithm, it's going to be the logarithm of something less than 1, which will give me something negative. So the two negatives cancel, and yes, I do get positive work, all right? If I compress to the same final volume, but I start with a bigger initial volume, I should get more work, and I see that happens here as well. If I start with the same initial volume and go to a smaller final volume, I should get a bigger work, all right? And that pans out as well. Another limit you could take is, what if I didn't compress it at all? What if the initial and final volume were the same? Then I didn't do any work, right? And according to this equation, I take the natural log of 1, which is 0. In that limit, this equation works. Another limit we could take is, what if we compress the gas to 0? Just totally compress it to 0 volume. Well, you can imagine as you do that, the pressure is going to go up to infinity, and I'm going to have to do an infinite amount of work to do that. If I let VB go to 0, the natural log of 0 is negative infinity, and I get an infinite amount of work I have to do. So those are just some tests I can do to make sure that my answer seems reasonable, and then I go ahead and plug the numbers in and hopefully get my answer. Units, Pressure times volume has units of work, so it looks, and this has no units, so it looks like my units work out. So there are your example problems. Hope you had a fun time.